So good morning, everyone. Here is my talk on establishing confidence and uncertainty in real-time systems. The work has been done with David Griffin and Benjamin Lesage as part of a project that we've been doing with Rolls-Royce, which is a knowledge transfer partnership aimed at improving the way that they will perform and analyse and develop real-time systems in the future. So a basic overview of the seminar is I'm going to introduce the baseline data that's being used for the assessment. I'm going to talk about the analysis that we did on that data in a number of stages. The first one being a black box basic statistical analysis of the data, and then a grey box analysis of the data where we looked inside the software and did a more detailed analysis than the black box would afford. This was done with a combination of machine learning and statistics to give us a deeper knowledge. And then finally, I'll wrap the talk up with characterising what we found out about the data and the software using the notions of known knowns, known unknowns, unknown unknowns, and unknown unknowns. So a brief recap of the TACO framework, which has been presented at the previous RTNS. With Rolls-Royce, we've developed a search-based framework for large-scale testing of industrial software. This uses simulated annealing and creates test vectors which are applied to software under test. The original work on this was presented at ECRTS 2016, and since then we've integrated it into a large-scale framework that allows Rolls-Royce to check out all the elements of their software system and one by one test them to establish the execution time data. The premise of that work has been that the data is gathered and then would be fed into things like RapidTime. The aim of the simulated annealing algorithm, and in particular the fitness function, is to provide confidence of execution time data through coverage. So it has been aimed at maximizing local path coverage in order to give us the best possible confidence. The reason for localized path coverage is that it is unrealistic to achieve full path coverage for realistically sized software. In the work in ECRTS, the function that it was used, which is called BCHLR, which is basically branch coverage with history and loops, was shown to be much more effective than other fitness functions in the state of the art, including just searching for execution time. So the result of this work is a vast amount of data from a full authority digital engine controller. So in the work, we've analysed close to 300 tasks, and this has been done both on the Vision core processor, which is the one that's used in flight, and then more locally at York on Pi 3B pluses. But the aim really of this work has always been to do execution time analysis. The result of TACO is a vast amount of data, which includes block level data, which is the number of iterations run on a particular test, i.e. we apply a test vector to the piece of software, and then we count the number of iterations of each block, and then a cycle count. So for each block executed, we know how long each block took on each iteration. And then at program level, we have a sequence of I points covered. An I point is an instrumentation point at the start of each basic block, and then the end from that and end-to-end execution time can be generated. Now, the aim of this work isn't so much to understand the fitness function. It isn't to establish a WCT, but it's more to understand the sufficiency of testing. So what in the previous work, what we showed is that with the fitness function we had, we achieved a better level of coverage and a more reliable execution time, whether we're doing it via high watermark or RapidTime. But here we want to understand the sufficiency of the data and whether more effectively, whether more testing would improve the results, and how much effort would be required to get that better evidence. So the sufficiency is judged in a number of ways: understanding the structure of the software through testing to enable accurate hybrid analysis along the lines of the approach that RapidTime does. And it was done in three principal stages: pure black box analysis, where we look at raw statistics; machine learning, depending on how you define this. Machine learning means many things to many people, but here I'm taking the definition as things that I can learn and establish about the software through testing and through data analytics. And then statistical analysis of the learned information. So here's stage one to give you some understanding of the software under test and the types of information we had. So the left-hand side of this graph over here is the spread of execution time of the piece of software. So for a particular execution time run, the degree of change we see in the execution time. So this basically tells us that the execution time for this piece of software ranged anywhere between 35,000 and 80,000. On the right-hand side, what we did is we looked at the measurement noise on samples. So what we did is we looked at particular test vectors run many times. So we identified across all the testing that we did, test vectors that were identical when applied to the piece of software. And then we assessed the range of execution times we got from that. So in the right-hand side graph, what we saw is for exactly the same test vector, we saw execution times anywhere in the range of 58,000 to 75,000. But most of the time it was in the range of 58,000 to about 63,000. So this showed that in general, we had a relatively low amount of measurement noise in our samples. Clearly the measurement noise here can come from a wide variety of features, such as the experimental setup, the processor itself, and potentially the RTOS that we were using within experiments. It's worth noting that in this work we used Linux because in our work, in other works, it was seen to be the most reliable. Then the next stage of analysis in the black box analysis was to establish what is the best balance between the number of runs and number of iterations. So the left-hand side graph shows the number of iterations is the number of test vectors each time. So what this graph basically shows on the y-axis for the left-hand side, it's got high watermark, and then on the x-axis, it's got the number of iterations. Now, what we see in this graph is that as the number of iterations increases, then the high watermark increases. But what we also notice is it's kind of a knee function where after about 20,000 iterations, what we didn't see as big an increase in the high watermark. So it's worth noting that high watermarks are the average over 25 runs of the search function. The right-hand side is a different assessment where for 50,000 iterations, we looked at the number of runs and whether the results are stabilizing. So again, we got the average high watermark on the y-axis, and we got the number of runs on the x-axis. And what we see in this case is, again, we see variability, but what we see is after about 25 runs, then things begin to settle down. So based on this, we could conclude that a good balance in terms of the number of runs and the number of iterations could be 25 runs and 20,000 iterations on each of those runs. So this gives us a baseline for going forward. Clearly, the more the better. And it's worth noting that for the right-hand graph, we did 50,000 iterations and established 25 runs was sufficient. But we went back and checked whether 25 runs and 20K iterations gave us a similar trend, and in fact it did. So we then started to do a black box analysis based on 100 trials and 50K iterations to assess convergence. Now, what we mean by convergence is, again, are we seeing different amounts of information? Are we learning anything new through the trials we performed? So basically, there's two graphs here. One is for goodness of fit via a KS test, and the right-hand side is the Earth movers distance, which is different metrics and which we believe in general is a better indication of whether there are differences in distributions. So for both of these graphs, we've got the relative metric that we're looking for, example, EMD for high watermark on the y-axis, and on the x-axis, we've got the amount of comparison data. So when it's in this graph, when it says 10%, what it means is we took 10% of the data we had, so say 10 trials worth of data, and we compared it with the other 90%. And what we looked at was whether we were seeing a significant difference. So what we saw in both graphs was we saw a relatively continual drop-off, i.e. in the metrics recorded, which basically said smaller and smaller differences were being recorded. But still, there were significant differences. And if you used a figure such as 0.05 for goodness of fit, by 50%, we still hadn't reached that level. So execution time didn't give us much confidence in convergence, but actually you might see that as a negative result and something bad about our search algorithm, but actually it was a positive result. And the reason for that is the way the search fit function was designed, it was actually trying to emphasize coverage. And by emphasizing coverage, it was actually trying to avoid convergence of execution time, because that would imply that we'd hit a local minimum and we were probably testing the similar path each time. So actually, even though this showed we were still learning information about execution time, we saw it also as a good thing for our fitness function. The next stage in the stage 2 assessment was to go slightly more grey box and look at significant factors, look at what we can infer from the results. So basically we looked at what we thought were significant factors, which would be things like execution time, loop counts, and number of eye points covered in the particular iterations. So in these particular graphs, we concentrate on box plots using the Earth mover's distance. So we had a number of trials. We did cross-fold validation, where we take, say, 10% of the comparison data and compare it with 92%, and we do that, say, 100 times. So in this graph, we've got two graphs. On the left-hand side, we've got EMD for eye points, and on the right-hand side, we've got EMD for loop count 83. And what that means is each loop in the software was given an ID. In this case, it was loop count 83. That does not mean that there's more than 83 loops in the software. In fact, there are very few loops in the software because of the way it's written. It's written in a very predictable fashion, but it just means that that was the identifier given to it by the test rig. So what this showed is, again, this showed a steady convergence. It showed as we use more test data that we were learning less and less, or there was less and less difference between effectively the training data and the test data. So from this, you might conclude that about 25% of the data would be sufficient, because at that stage, we've effectively, the amount of differences has reduced substantially. That interestingly corresponds to the fact 25% of 100 runs is 25 runs, and that was what we concluded from the execution time. So we're seeing some similar trends here, but at the same time, we're not getting an override message that we fully understand this piece of software, even based on a significant amount of testing. Some other graphs that we found interesting when we go grey box and looking at the information, and also emphasizes the challenges in understanding software. So on the left-hand side here, what we have is the frequency of the number of iterations where both the eye points and path length were maximized. So what we see in this graph is basically, it's for particular iterations, well, across the set of iterations, we look at what is the maximum eye points and what's the maximum path length. And then we look for each iteration, say, have we maximized both of those at the same time? And as you can see, the frequency count implies that only one or two times did we see both of those maximized. It's worth saying the frequency count that shows how many iterations within a run that occurred. And so what you see in here is in one run, we saw 3 iterations, in another run we saw 9 iterations, but most of the time we didn't see any iterations that maximized both. So again, this implies we very rarely, in the runs we did at the simulated annealing algorithm, hit both of those at the same time. The right-hand side graph is really informative, and it tells you a lot about the software and the challenges that would be taken in testing this software and fully understanding it. So basically, on the x-axis on the y-axis is the path length, so the number of eye points covered during an iteration, and on the right, on the x-axis is the execution time, and then the color coding actually tells you the number of loop iterations. So if you take the set of loops and you look at the number of times they iterate, it goes up to a number of 162. So this basically says if you add up for a particular iteration or a particular test vector, the amount of times loops were all the loops in the software were iterated on that, it could be up to 162. And as you can see, this graph shows that the software has a multimodal characteristics. It shows things like that in general, the higher execution times tends to be more yellow, which implies more loop iterations. It also has a longer path length, but actually that's not always the case. So we see some cases where loop iterations as low as 47 gave very long paths and very long execution times. So this all suggests that confidence is converging, and having certainty in your testing it is challenging. So we also tried to establish whether infeasible paths exist for reasons of time. I won't go over this in too much depth, but basically the left-hand side says that in how many I-point pairs basically remain on an individual run. So what we mean by that is we looked at I-points and see whether on a particular iteration, if point X and I-point X and I-point Y were both visited on that run. And then by what we showed through the whole analysis is by run 28, there was no I-point pairs that remained. So basically what this meant is an I-point pair that's never visited on the same iteration could be infeasible. Doesn't mean it is infeasible because testing is never conclusive, but it could be infeasible. So it took 28 runs to eliminate all the I-point pairs to show that there was no infeasible paths for this piece of software. The right-hand side is how many of those remain for each one. So there's a frequency on the y-axis, and in general, what we saw is for most runs, actually there was a significant number of I-point pairs that still exist. So it could be up to, say, if the result on this graph was 1,000, it meant that there was actually 1,000 I-point pairs that hadn't been seen together. But over a process of a number of runs, we eventually eliminated all the combinations. Again, this is a suggestion that our software aims to achieve coverage. So if it isn't achieved in one run, it would be achieved in the next run. So overall, the work showed execution times had not converged much, but other significant factors had to a greater degree. This was a positive result for the originally designed fitness function, but the objective of this work was not to show that the fitness function was outperformed others, because we'd done that previous work. What it showed is understanding confidence and convergence is challenging. We did a vast amount of analysis that isn't shown in the presentation or even in the paper. And it was actually hard to fully understand and have an oracle and a definitive set of knowledge of, have we done enough testing? Would testing reveal more information? Well, of course it would, but would that extra testing be worthwhile? So even after large scale testing, and remember 100 runs and 50,000 iterations, is actually over 5 million test vectors applied, and many of those are different. We were still left with significant unanswered questions. Applying statistical analysis in a black box manner told us very little. Whereas going deeper, learning details about significant facts like loop bounds, number of I-points covered, etc., and then applying statistics on top of that was more useful, but still not. We're still a long, long way from fully understanding confidences and uncertainties. So some of what we can do can be thought about in terms of Rumsfeld and NASA popularized. So known knowns, known unknowns, unknown knowns, and unknown unknowns. These are useful ways of thinking about the lessons learned, particularly in this type of work. So known knowns are only what we have observed, e.g. the maximum observed loop bounds. Known unknowns is what we know that we probably don't know, e.g. the actual maximum loop bounds. Unknown knowns are we haven't seen something but don't know if it could happen, e.g. a single iteration maximizing all loop bounds. We in most of the trials we never saw that happen, but we suspect it could. And unknown knowns are events judged implausible, and this would be something like an error changing the loop bounds in the software and therefore undermining the previous evidence. So summary in future directions, determining WCTs for predictable software on a less complex platform shown to be difficult. But it's much harder to determine when enough testing is done. Notions that may be useful here are things like as low as reasonably practicable and the French equivalent here. And the message here is, could we learn more as low as reasonable practical would the cost of further testing, for example, be disproportionate to the benefits again, and whether doing something, and the French equivalent is basically at least as safe as before. So basically we've changed something in the system, have we undermined the safety? And again, moving to a less predictable platform, that's something you have to consider. There are significant unknowns, and as part of this, if we move to something like multi-core, it becomes an even more formidable problem. Remember, we're looking at worst case execution times here. If we expanded this problem to a much more complex testing and an analytical problem like multi-core, then it would become much harder to determine whether the level of confidence and uncertainties we have. Other key points are other forms of machine learning may help, but similar issues may arise. So our view is resilient designs must be the answer, but we still need to know resilience to what. So we still need to understand where we have confidence in our data, where the significant uncertainties may exist, and then we build in appropriate resilience to deal with those. And this type of work, what we have done, could inform us where the errors are more likely to exist, where our testing may be weakest, but clearly it's not definitive. Acknowledgements. So members of the York Real-Time Systems Group, Rolls-Royce for years of support, inspiration and access to real systems. A number of projects that we have funded at the moment, High Class, which is a project on multi-core, ATICS, which actually funded the work where TACO was developed, and Huawei and Project Mocha, where we're taking some of these concepts further. Equally, I'd also like to thank the members of WashU for various stimulating discussions on my study leave, and equally important, Space to Think, which was a vital part of going on any sabbatical. So thank you very much for your attention and any questions.